4x, and that whole thing was to the 7th power, given time, energy, and sufficient monetary motivation, I could probably convince you to multiply that out. But nobody wants to do that. Luckily, chain rule is going to help us out of that problem. So most formally, we can think about this as having an inside function that we could call u of x. I'm not going to bother writing out that notation. I'm going to jump straight to, let's find the derivative. So if I wanted to find f prime of x, chain rule says I have some stuff in parentheses, and it's raised to the 7th power. So when I take the derivative, I'm going to get that stuff in parentheses. I'll bring that exponent down and have stuff in parentheses raised to the 6th power. Now what was in here was 3x squared plus 4x. The chain rule component is that I'm now going to multiply by the derivative of the inside function. So our inside function here being 3x squared plus 4x, that derivative would be 6x plus 4. And we don't have to do anything else with this. We can just walk away. That's our derivative. I don't know that we did any chain rule problems involving trig, but I want to do some chain rule problems involving trig. So a couple of common notation things that come up with our trig functions. And I know we did at least one of these previously. So if my function, if I write this as cosine and I put a 7 here and an x, notation-wise, this means, so I'm not taking a derivative yet, I'm just rewriting it. This means that I have cosine of x, and that entire thing is raised to the 7th power. So if I follow this same procedure to find that derivative, once again, I have something inside of my parentheses raised to the 7th power. And when I take that derivative, that 7 will come down in front. And then I'll have the stuff in parentheses to the 6th power. This time, that stuff in parentheses is cosine of x. And when I multiply by the derivative of the inside, that inside function derivative is negative sine of x. So taking the second derivative means I'm starting with the derivative that exists. We're going to take one more derivative. When I look at this, I see 1, 2, 3 pieces being multiplied together. But because that 7 is just a constant, I'm not going to treat this as a triple product rule. My 7, I'm going to use that constant multiple rule. That 7 is just coming along for the ride with me. But I will need to do a product rule, and my product is going to happen between cosine of x raised to the 6th power and that negative sine of x. So if I get this going with product rule, that 7 is coming along for the ride as that constant multiple rule, and I'm just going to give myself plenty of space. And I know that if I'm doing a product rule, I'm going to need to start by taking the derivative of the first piece. Well, that first piece, I have something in parentheses raised to the 6th power. So when I take that derivative, I'm going to end up with 6 times the something in parentheses raised to the 5th power times, chain rule says, I had something raised to the 6th power, so I need to multiply by the derivative of the inside, and that's going to be that negative sine of x. Then, again, product rule-wise, all of that was just the derivative of the first piece. So I'm going to multiply that by the second piece unchanged. Since it's a product rule, I know we're adding. And that second piece in my product rule, I'm going to leave that cosine of x to the 6th alone, and then multiply by the derivative of negative sine of x. Since the derivative of positive sine is positive cosine, the derivative of negative sine will be negative cosine. So this will be times negative cosine of x. Again, I would walk away there, but if you wanted to, we could then look at all of that and I suppose factor out. They both have a cosine x to the 5th that you could factor out if you wanted to, but I would really just stop and walk away. And all I want to do is take the derivative. So my instructions here are going to be to find, oh, let's take 2 derivatives. Why not? So let's find the first and second derivative. So if we're going to find the first and second derivatives, I'm looking at this function, and this says secant of 3x. That's how we would read it out loud if we're reading that in words. And if this is secant of 3x, then that 3x is secretly a function within the secant. So when I go to find that first derivative, I know that the derivative of secant of x is secant of x times tangent of x. Well, calculus can never change the argument of a trig function, meaning calculus alone can never change what's inside of a trig function. When I write down this derivative, my derivative is secant of 3x times tangent of 3x times, chain rule says, because I have an inside function, I need to multiply by the derivative of what's inside. And the derivative of 3x is 3. And really, there are 2 places where students make mistakes on this problem. Either forgetting the 3 at the end or writing the derivative of secant of whatever as just secant x tangent x. But we need to make sure that we bring that inside function along with us when we're taking derivatives. So I'm going to give you a minute to find that second derivative on your paper. But since it's a product rule, I'm going to need derivative of my first piece and the derivative of secant of 3x. I have a function inside of my secant, so I already know I'm going to need to use chain rule. And then I'm going to think about the derivative of secant of something is secant of that something times tangent of that something. And then we'll go ahead and multiply by the derivative of the inside, which is 3. Then, because of my product rule, I'm going to multiply by tangent of 3x without taking its derivative. Ooh, I might run out of space here. Plus, we leave our first piece alone, so we'll just have secant of 3x times the derivative of our second piece. And the derivative of tangent of something is secant squared of that something. And then that chain rule piece means I need to multiply by the derivative of the inside, which is 3. So as a reminder, if I have f times g times h, and I take the derivative, and there are different notations for taking that derivative, this would be the same as in Kuba's notation, having a capital D of f times g times h. Either way, that triple product rule looks like f prime times g times h plus f times g prime times h plus f times g times h prime, right? It's 3 letters, we write it 3 times, and we chase down the derivative. So what if my function that I was working with, that I wanted to take the derivative of, looked like So this is another notation that says take the derivative. So what if I wanted to take the derivative of, let's say 3, too many 3's. I don't want so many 3's. Let's say this looked like 5x squared plus 7, and that whole thing was cubed. Well, before we learned chain rule, we had two options for trying to find this derivative. Option 1 would be to write that as 5x squared plus 7 times 5x squared plus 7 times 5x squared plus 7 and do the algebra to multiply all of that out. Another option is to write it that same way. So write it as 5x squared plus 7 times 5x squared plus 7 times 5x squared plus 7, but apply the triple product rule. So each of these, so if I think about this as an F times G times H, I'm going to go ahead and apply the triple product rule to this and see what happens. I did not leave myself a ton of space, but I think I can squeeze it in. So for the first part of my triple product rule, and I'll just give myself a plus and a plus here. So for the first part of the triple product rule, I need F prime times G times H. So when I take the derivative of F to do the F prime part, I'll have 10x plus a 0. So I'll just write that as 10x. And then I'll have times 5x squared plus 7 times another 5x squared plus 7. The next part of my triple product rule, I need to leave F alone. So F was right here, so I've got 5x squared plus 7 times, this time I need to take the derivative of G, and the derivative of G is 10x. And then I'll leave the H alone, 5x squared plus 7. And then for the last part, I leave F and G alone, 5x squared plus 7 times another 5x squared plus 7. And then I need the derivative of H, and the derivative of H is 10x. So I may not have mentioned it in here. Mathematicians, they like shortcuts, as long as it's a shortcut that's mathematically sound and works in every case. Some mathematician looked at this thing and said, wait, there's an easier way to write that. Each of these has a 5x squared plus 7 times another 5x squared plus 7. Well, we can write that differently. So I can take that 5x squared plus 7 times another 5x squared plus 7 and write that as 5x squared plus 7 squared. And then we still have times the 10x over there. And this piece, I have a 5x squared plus 7 and another 5x squared plus 7 times that 10x. And this piece, I have a 5x squared plus 7 times another 5x squared plus 7. So we can write that as squared times 10x. And then all of these are identical. And I have 1, 2, 3 of them, meaning I have 3 of that 5x squared plus 7 times 10x. So clever mathematicians said, hey, we should give that a name because that's, squared, because that's a pretty nifty shortcut. If I start out with something raised to a power, this repeated product rule is always going to lead us to the same place. We could treat that something raised to the power as if it's kind of its own function. And if it is, then we're just going to use our power rule, bring that 3 down in front, leave this alone, raise it to the 3 minus 2, and then multiply by the derivative of the inside. So that's really all we're talking about when we talk about chain rule. First of all, if I'm going to find the equation of a tangent line, I need a slope and a point. Well, I gave us half of a point. To turn that into a whole point, I need to know what y equals when x is 1. So the first thing I'm going to do is to take that and make it a point. So it's going to be 1 comma something. So if I plug in 1, 1 to the 4th is 1, 3 plus 1 is 4, square root of 4 is 2, I'm at 1/2. So 1 comma 1/2. There's the point I'm at. So if I'm thinking partial credit, it said I need the equation of a tangent line. I'm already at y minus 1/2 is equal to m times x minus 1. Give me that partial credit in case I run out of time on the problem. Now, tangent, if I need a tangent line, that means I need to take a derivative. So I'm going to come back over here to this function and say, why, that's messy. I wonder if there's another way that I might be able to rewrite it to clean it up a little bit. Well, I know that a square root means that I have a 1/2 exponent. And I know that since it's in the denominator, I could write that as a negative 1/2 exponent. So my function here would look like 3x to the 4th plus x to the negative 1/2 power. I know that if we're going to take a derivative, I have something trapped in parentheses. I'm going to have to use chain rule. So I'm going to give you all a minute to take this derivative on your paper. Some stuff raised to a power. So when I go to take that derivative, I'm going to end up with the negative 1/2 down in front, and then copying down exactly what's inside my parentheses. Negative 1/2 minus 1 is going to give me negative 3/2. And then chain rule says I'm going to multiply by the derivative of the inside function. So I'm going to multiply by 12x cubed plus 1. Getting back to this question, to find the equation of the line tangent to the graph when x equals 1, that tells me that I need to find my slope when x is 1. So here, my slope is going to come from f prime of 1. And I'm just going to go ahead and plug that 1 in. So 1 to the 4th is 1. So that's 3 plus 1, and I've got 4 raised to the negative 3/2 times, plug in the 1 here, I'll have 12 plus 1, which is 13. We could leave that alone and just plug it in there as a slope, or we can make that, we can clean that up a little bit. It's kind of up to you, but I'm going to go ahead and clean that up to a number. You can decide if you would just walk away and grab that whole thing and put it up there. 4 to the negative 3/2. That's a negative, a cubed, and a square root. So I got to do all three things. I'm going to start by dealing with the square root. So the square root of 4 would be 2. If I cube that, I'll get 8. And the negative exponent turns that into a 1/8. So that's the same as negative 1/2 times 1/8 times 13. So my final answer over here with a slope, I'm going to have y minus 1/2 is equal to negative 13/16 times x minus 1. So far, the chain rule problems that we've done have been kind of one function inside of parentheses. This is sort of layered functions inside of parentheses, or it's a chain of functions. It's a hot mess, but we can make it through this. First thing that I want to do is to rewrite that square root as being some stuff to the 1/2 power. And because I know I'm going to need all the board space I can get, I'm just going to go ahead and do that for us and say that I've got this stuff raised to the 1/2 power. When we're working on chain rule problems that kind of have functions inside of functions inside of functions, we work from the outside in, like we're peeling layers off of an onion. And when I work from the outside of in, for me personally, I think one of the hardest things is kind of keeping track of what we've already taken derivatives of. So I actually give myself check marks along the way so that I remember I dealt with the derivative of that part. So if I stand back and I look at the entire function, I've got stuff to the 1/2 power. So when I get going on my derivative, that first thing is going to be that 1/2 of all of that stuff. I'm going to have to write small, all of that stuff to the negative 1/2 power. And now I have dealt with this 1/2 power. I took its derivative. And I'm going to copy down exactly what we have in here. So I've got tangent of cosine of x to the 10th minus 3x squared. So if I think about having peeled off that layer, then the next sort of function that I'm looking at where I have stuff trapped in parentheses is that tangent. And the derivative of tangent is secant squared. So the derivative of tangent of some stuff is secant squared of that stuff. So the derivative of that tangent, I was trying to do something tricky with my colors. It's complicated. I'm not going there. Derivative of that tangent part is secant squared of the stuff. So I've now taken the derivative of the tangent. And I'm going to copy down the stuff that was inside of it. And the stuff that was inside of it, cosine of x to the 10th minus 3x squared. Next part, I've got these parentheses, and I made this one complicated. I've got these parentheses, and inside of those parentheses, I have two pieces that are being subtracted. So that means I'm going to treat each one separately, take the derivative of this, and then subtract off the derivative of this. So I'm going to go ahead and give myself a new set of parentheses. And I'm going to do the easy part first, which is to take the derivative of 3x squared and get 6x. Now I've got to go back and deal with cosine of x to the 10th. Well, the derivative of cosine is negative sine. So the derivative of cosine of some stuff is negative sine of that stuff. So I've taken the derivative of the cosine part. I need to copy back down that x to the 10th. And then I'm going to multiply that by my final thing. I've got check marks everywhere except on that x to the 10th. And the derivative of x to the 10th is 10x to the 9th. That's seriously like as bad as I can imagine a chain rule problem getting for you. I think that's way, and if you're in Ben's class, I'm freaking out right now. Like, if you have a chain rule problem on that quiz tomorrow, it's not going to be a crazy chain rule problem. It's going to be one of the more straightforward ones where I've got stuff in parentheses raised to an exponent, or I have a trig function with something inside. Oh, so another one of these crazy kind of problems, or the more straightforward-y kind of chain rule problems? The crazy kind. Okay, for sure. Let's do another crazy one. Let's look at the square root of, yeah, I don't know why square roots, but they show up a lot in general problems for some reason, but let's do the square root of x plus the cube root of x plus the square root of x. And I want to find f prime. So the first thing that I want to do, and this is true anytime we have roots or radicals in the problem, is we want to rewrite those as fraction exponents. So the first step here is to rewrite this to say x plus some stuff, whole thing to the 1/2 power. So I rewrote that exponent. And then this part in here, the x plus square root of x, that's a cube root. So that'll be some stuff to the 1/3 power. And then in here, I'll have x plus x to the 1/2 power. Now, if we go to take our derivative, I've got stuff inside of stuff inside of stuff. So I know that I'm going to start at the outside, and that very outside function is that I've got stuff to the 1/2 power. So when I take that derivative, I'm going to end up with 1/2 times all that stuff to the negative 1/2 power. And I've got x plus, oh, I don't even need that much space. I've got x plus 1. I can't even write. Just trying to copy the same thing down. X plus x to the 1/2, whole thing to the 1/3 power. And then subtracting 1 from 1/2, I get negative 1/2. And then, so I've taken the derivative with the 1/2, so I'm walking away. Now, my next layer in, so if I get rid of these parentheses, then I have x plus something. And again, when we're doing derivatives, if I've got addition or subtraction, then we treat the parts separately. So I'm going to get some big parentheses here because the derivative of x will be 1. And now I need to worry and focus in just, I took the derivative of the x part. Now I'm going to focus in just on this piece. And on this piece, I've got another chain rule. So I have something in parentheses to the 1/3 power, and I'll get 1/3 times what's in parentheses. 1/3 minus 1 will put me at negative 2/3. So now I've taken the derivative of that 1/3 power part, and the only thing left to do is to take the derivative of the inside, that x plus x to the 1/2. So derivative of x is 1, and x to the 1/2, when I take that derivative, I'll have that 1/2 come down in front and subtract 1 from the exponent. Bam, there we go. Here, I do have a chain rule inside of a chain rule, right? But this is a little bit more straightforward and also one that's easier to miss. Anytime I have a number here, like right after the trig function, I'm always going to choose to rewrite that before I take a derivative. Because this is the same as cosine of 5t, whole thing squared. And it's that whole thing squared part that is going to help me out with this derivative. It looks like someone sat on an x, not that it was a t. So f prime of t. So this is a chain rule inside of a chain rule. But my overall outer function is some stuff squared. So that's going to become 2 times that stuff to the first power. And I don't usually write the 1. You could, but I don't usually write the 1. So I've now taken the derivative of the part with the 2. So I'm giving myself a check mark. And I'm going to copy down exactly what we had, cosine of 5t. Chain rule says I'm going to multiply by the derivative of the inside. Well, that next function that we would hit is the cosine. And the derivative of cosine is negative sine of the stuff. So I took the derivative of the cosine. Finally, I'm going to multiply by the derivative of 5, because that's what the derivative of my 5t is going to give me. And now I've taken all of the parts of the derivative. But I haven't answered the question yet, because I asked us to find f prime of pi. So now I'm going to come back in and say f prime of pi. If I plug that in, that's 2 times cosine of 5 pi times negative sine of 5 pi, whole thing times 5. Well, let's see. Cosine of 5 pi. So, see if I can get this right. No, I was going to try to swing my arms around in circles, but here I'm at 0 pi, 1 pi, 2 pi's, 3 pi's, 4 pi's, 5 pi's. So I'm over here. So cosine of 5 pi is negative 1, but sine of 5 pi is 0. So overall, that's going to be 0, which incidentally also means I have a horizontal tangent line.